So now what we're going to do is we're going to write the code for this amortized analysis, and I'm going to be throwing in a few extra challenges while actually coding this. So now we are writing the code for this, and what we have is a main function, but apart from that we also have a class which is a dynamic array. Okay, and as we discussed, this is a class which is going to be containing an array itself, so that will be int a of size, let's say 10. This is what we are starting with, and as more and more inserts are done on this, we are going to be understanding whether the size of the array has been exceeded and we need to double the size of the array or not. Okay, so all that will come in. So taking that in consideration, what I'm going to do is there's a variable size which this dynamic array is going to contain in it. All right, and initially the size is, let's say, 10. In fact, to simplify, I think I'll just keep size as 1. All right, this was the video example that we had, and this is what is going to be. So there are two operations that I can think of. The first one is add into this array, right? I want to add an element because it's an integer array. I'm going to be adding integers into this. So a of, now I also need a counter as to the number of elements in this array. So I'll just call that a counter, and what I can do with this is I can just add to the position of the counter the element, and to simplify I can just increment the counter once this is done. Alright, pretty simple. Just add the element to the current position of the counter and then increment that. Now this is the only operation that you need, but of course we would like to print the array. So what I can then do is just say that I need a toString method. This is all specific to Java, and it's pretty interesting if you look into it. But I want the array printed, I want the size printed, I want the counter printed. Pretty useful for debugging stuff. All right. So now when I'm adding, one of the possibilities is this possibility, the simpler possibility. Just add to the counter and you're through. But what if you have the counter equal to the size of your array? All right. At this point, what has happened is you've actually hit the threshold condition. You have filled up your entire array. You cannot go further. You need to double the size of your array. So I'm going to say just double the size of this array. Counter stays exactly where it is. What about a? Well, it needs to be a new array now. So a is a new array of this new size. But then we just lost all the information that we had in the old array a. Okay, so what we need to do before this is to actually use a temporary array, right? And a will be assigned to that. But first we are going to be using this temporary array and then copying all the elements of a into this temporary array and then assigning, array a to this temporary array. All right. So the size has already been doubled for all the elements in a. I want the temporary array to be containing, to copy the elements in a. Alright, and this is quite simple, but there's a inbuilt function in Java which actually allows you to copy arrays efficiently. So system.arrayCopy just copies an array from a given position to a given position. Alright, pretty useful again. Simple stuff. Alright, now I'm now able to add elements to this array in the same asymptotic complexity that we talked about, rather the amortized complexity that we talked about. So I can also print the array. So let's just do that. Let's have a main function in which I'm going to be inserting elements, and every time I actually need to double the size of the array, I'm going to say doubling size of array. All right, that's a pretty big deal for me. And after that, I can just take the element at this counter, set this, and then increment counter. Okay. So initially, of course, the size is 1 and counter is 0. All right. So I'm going to be taking a buffered reader to read in my input. This is standard stuff in Java, especially if you have been comparative programming for some time. This is all standard stuff. Fine. In fact, if you want a brief understanding of input output and Java, you can have a look at the comparative programming Java playlist. That's pretty useful for this kind of thing. All right, so I'm going to be reading in input now. So int input is equal to whatever is being sent in here. I'm going to be converting that to an integer. And of course, some people find this pretty verbose. It is actually extremely verbose, but I am comfortable with this. And also, after a certain point of time, you kind of like the clear way in which Java actually specifies things. So enough, promotion about Java. Let's get to the dynamic array. We can define the dynamic array here itself. All right, and yeah. So the dynamic array is going to be added to. The reason I'm making these variables private is because I don't want them accessed from outside the array. All right. So now I'm adding the element which is input, and I'm going to go on doing this while the input, or rather, let me just assign this over here. Yeah, I'm just gonna, so the input is right here, while input not equal to -1, I'm going to be taking an input. All right. Okay, so let's just recap what I'm trying to do. I'm taking input, constructing this dynamic array, and then inserting elements into it. So that's the add bit, right? And I'm going to go on doing this. This is just the input and output bit. Okay, you can ignore this entire bit. What it's doing is just taking input and outputting the array in the end. So I can s out dynamic array, and that internally will call this toString function. Okay. Now, inside the dynamic array, what I'm doing is I'm just taking the size to be 1 initially. Every time I do an insert, I check if the current size of the array is equal to the position in which the element should be inserted. If that is the case, then I have actually there's an overflow, all right? And what I need to do is I need to double the size of my array, which is going to be happening in this bit. Okay. Now, if not, then I'm going to be just taking the element and putting it in the counter's place. That's perfect. Doubling is pretty easy. I just double the size of the array. I take a temporary array of double size. Yeah, you're seeing it's doubled here, so double size. And then I'm just going to be assigning the old array to this new temporary array after the copy has happened. Fine, pretty simple. Let's try running this. Okay, it's taking some time because I think it's been a long time since I've actually used this project. Okay, what do I do? I think I'll insert 3. I think I'll insert 6. There you go. It doubled the size of the array. And then I'm going to say I'm going to insert 1. Again, it doubled the size of the array because it became 1 and then 2. So now let's try 5. Nothing happened as expected. 4, doubling the size of the array. 1, 7, 9, 3. It doubled now. So you're seeing that the doubling is becoming less and less frequent. So now you're seeing a lot of inserts just went in and then it had to double. So you can see it's exponential actually. I need to exponentially increase the number of elements I'm inserting for it to double the size of the array. And that's the reason why it's such a beautiful concept, because in an amortized way, in an average way over an extended period of time, this is going to be, oh I think I missed one. But you can see that what's happening is I by mistake entered just a space, so that's not an integer, and that's why there's an exception. But yeah, it's working pretty well. It's doubling the size of the array, rare enough, so that our overall time complexity is still order n. Okay, so this is working out quite well. In fact, you know what, I'm just going to run that again so that you guys can see uh, how it looks. 7, 8, and this was a mistake by the computer. It didn't get time to actually type this out, I think so. 10, 11, and you'll see that the size of the array is pretty large. So if I enter -1 now, you can see that the dynamic array is going up to 11, and then there's space for 12, 13, 14, 15, and 16 over here. Okay, and that's the number of elements it will take before it again doubles. So counter is 11, that makes sense, and the size is 16. Okay, perfect. So now for a new challenge, what I'm going to do is I'm going to actually allow deletions in this array. Okay, it's going to be fun, and let's see if we can actually do that. So deletes are allowed, and deleting will be at a particular position. No, not really. What I'm going to allow is deleting from the end of the array. Okay, the reason for that is because I'm going to try to keep this dynamic array as simple as possible. There's only insertions at the back end, and there's only deletes from the back end. So in fact, we don't even need this parameter for delete because we are just removing from the end of the list. Now, interestingly, delete is going to be just doing this, reducing the number of counts in the array. We don't need to clear garbage. But to make things obvious, I'm just going to make the element at counter set to 0. So that is like removing garbage. And our array is not going to be allowed to have elements equal to 0. So sometimes we are going to remove from this dynamic array. So I think delete is the word that we have used, and it doesn't have any parameters, of course. So if the input is less than 0, then I delete. Otherwise, I do this. Alright. So there are two types of operations. We have delete and add, depending on the input that we have. So if it's less than 0, then it will delete from the array. Also, if the counter is actually greater than 0, that's the only time we need to actually perform this operation, right? Is there anything else that you would like? Well, let's see something which is obvious. So every time we are deleting from the array, now what's going to happen is the counter will be decremented and the array position will be set to 0. So I'm going to be inserting elements 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now at 9 we have an array of size 16, and now I'm going to start deleting elements. So I'll just zoom into this. -1, -1, -1, -1, -1, and so on till, let's say, I'm bored of deleting elements and I just exit the program. Now you see that this array has just 1, 2, 3, and then all zeros over here. So the counter is 2. Okay, that's odd. Oh, all right. Actually, this is how it should be. Well, fine. It's all right. It doesn't look nice, but what's happened is there's a small bug in the program. I'll just run it again. But I'll take a small example now, I think. Yeah, well, I don't need to because it's turned out pretty well. So you see that I doubled the size of the array quite a few times, and now I deleted a lot of elements, and yeah, the counter here is again 2. That's great. So I have just 2 elements in this array, as you can see, but the size of the array is 16. All right, so that's not nice because I have a very small space requirement, but I'm wasting a lot of space over here just because I had a poor strategy earlier of doubling my elements every time I get an insertion. So is it a poor strategy? Let's have a look. Let's try to save space on deletions, and the most obvious way that you can save space is to use some of the logic we have over here, right? Instead of doubling the size of the array every time we overflow, I would say if the size of the array is equal to half of the elements that you need, is equal to actually double the elements that you need. So to make it a little more obvious, if the size of the array is double the elements that you need, I'm going to half the size of the array. So halving the size of the array. In fact, I think this is more logical, so I'll just do that. So size by 2, length of the array by 2 is equal to the number of counter elements you have. I have half the elements extra. I'm just going to half the size of the array. Okay, and instead of doing this, I'm going to be doing this. That makes sense. We have a temporary array in which we will be moving all our elements and then finally assigning the current array to this temporary array. All right, makes a lot of sense, I think. Okay, so now what do we do after having deleted this element and also updating the size of the array? Let's see if our new logic is a good idea. Saving space. Interesting. So I insert one element, two element, it doubles 3, 4, 5, 6, 7, 8, 9, and it doubled the size of the array. Now have a look. If I insert negative elements, then it deletes. Basically, that's a command for delete. So I just half the size of the array. But you see, this is a heavy operation. This operation actually requires size by 2. So let's try to analyze that. Size by 2 operations, which is actually setting this temporary array plus the length of this. So again, that is size by 2 and nothing else, plus the deletion itself, which is plus 1. So overall time complexity of this is size plus 1. All right, and size is in the worst case up to size n. So what we have done is we have just halved the size and we have also doubled the size just before that. Now I insert a new element and it doubles the size again. Okay, the size has become 16. Now I remove the element number 9. Again the array is halved to 8. These are all heavy operations and I can just go on doing this all day. You know, halving and doubling the size of the array. Oh, I just deleted an extra element by mistake, but nothing to worry about because if I insert 2 elements, again it doubles the size of the array. So what's happened is for every 2 elements, I require order size operations, and that is pretty bad. Okay, because order size for every 2 elements is going to be n into size, which is in the worst case around n, and this will be n squared. I know that this is not a very deep understanding of the complexity, but you can work this out and you'll see that order n squared is the time requirement for this kind of an array, or a dynamic array. So this is pretty bad. This is not a good strategy that we can have. I thought about this today morning and it took me some time to come up with this. In fact, then I went on the internet and I kind of verified that this works. The size of the array becoming half is not optimal. What you can do is you can still borrow from the previous strategy of saving elements. All right. So when there was an overflow, you double the size of the array. Now what you're going to do is you're going to make sure at least double the size of the array, is always kept. So if you're deleting elements, you will never have a scenario where you need to insert and you don't have at least twice the current size of the array. That's the logic for deleting elements. All right. So when you're deleting elements, half the size if you have more than 2x space requirement after deletion. All right, and simply put, instead of going for size by 2, what we then need is size by 4. Okay, what happens with size by 4? 1, 2, 3, 4, 5, 6, 7, 8. And when 9 comes in, we double the size of the array. But let's not get there. Let's say that this is what your array is. 1, 2, 3, 4, and then 4 elements left. If I delete this element and I try to halve the size of the array, that may not be the best thing to do, because now 2 more insertions and I'll need to double the size of the array. So I don't do that. I instead wait till 3 becomes 0. And now I know that even if I half the current size of the array, I'll have half of the remaining elements still left to insert elements into. Okay, this is pretty important. And that's the reason why once the number of elements in the array become 25% of the current size, which is size by 4, then what I'm going to do is I'm going to half the size of the array. All right, that makes sense. After halving the size of the array, I can insert 2 more elements, so 3 and 4 come in, and then when 5 is coming in, I again double the size. Now, why does this work compared to the previous strategy? It seems pretty similar, but actually no. When I'm moving to this, I actually move n by 2 elements. So I'm doing n by 2 operations basically. And to be precise, it will be size by 2 operations to the left, which is deletions. Then I'm doing size by 2 operations to the right, which is size by 2 insertions. After all of this, what I get is this deletion, which is of order size. And again, when you're doubling, again, it'll be the same thing, order size. So with all these size by 2 operations to the left and to the right, so overall size number of operations, I'm doing extra order size movement. So for order size number of operations, I'm moving order size extra. So overall the complexity becomes order size plus size, which is still order size. All right, and because size is actually n, we have order n as the worst case. So what we have done now is deletions and additions both combined as a set of operations that we need to perform in our dynamic array take amortized time complexity of order n. All right, that's the beauty of this algorithm. It works in order n amortized time, not per query, but overall extended period of time, order n. So let's just run that and see how this works. Okay, so I'm going to insert elements now. 1, 2, 3, 4, 5. Okay, 5 caused a doubling, so 6, 7, 8, and 9. And now I doubled the size of the array. Now what I'm going to say is I'm going to delete an element. You see that nothing happened over here. I'm going to delete another element, another element, another element. Careful, another element should probably reduce the size of the array. Exactly, half the size of the array. To what? Well, I just deleted 5 elements. So the current size became 4 and the size of the array was 16. So that's the reason why it halved the size of the array. In fact, I should probably print out the size. Yeah, that'll be a wise thing to do. I don't know why I didn't do that earlier. But yeah, if I print this out, then we can literally see how the size of the array is shifting. So from 1 to, okay, the size of the array was 1, it just doubled. 3, 4, 5, 6, 7, 8, 9. So the size of the array was 8, it has become 16 now. And now I remove elements to see half the size of the array. From 16 it becomes 8. And if I quit now, then I'll see that there are just 4 elements. You can see the counter itself over here, and the size is 8. But it didn't half the size when the size was 8 itself. It waited for some time till the load factor became 25%, right? So that there is at least half the elements extra in the array for further insertions. And this is done so that amortized, the complexity is boiled down to order n time. All right, so this was a little interesting. The entire dynamic array concept is actually very interesting. I'm sure you have doubts if this is the first time you're actually working with dynamic array, and if you can just post them in the comments below. If you have any suggestions for further videos, you can post them in the comments below again. And the reason I'm actually working on amortized complexity so much is because we are going to be taking parallel binary search pretty soon. So I just want our concepts on amortized complexity and other concepts pretty clear before we start off with parallel binary search, because that's a very advanced topic. So best of luck, and I'll see you next time.